आपका YouTube चैनल शंकर कोचिंग में आपका स्वागत है। मैं प्रोफेसर प्रेम शंकर आज 12th क्लास के स्टूडेंट्स को फर्स्ट चैप्टर मैथ्स का फर्स्ट चैप्टर रिलेशन एंड फंक्शन पढ़ाने जा रहा हूं। आप इस वीडियो को अंत तक देखें और कोई डाउट हो तो उसको कमेंट बॉक्स में दें। अगर आपको मेरा ये वीडियो पसंद आता है तो उसे लाइक करें, सब्सक्राइब करें और अपने फ्रेंड्स के साथ शेयर करें। चलिए वीडियो स्टार्ट करते हैं। So let us start the chapter relation and function. The first one, I will give the introduction of this chapter, then we will discuss relation, then we will discuss function, and then we will discuss the binary operation. So in the introduction portion for the relation and function, let us suppose two sets are given, means A is the set of all the student of the class 12th, and B is the set of all the student of class 11. And suppose we want to discuss few things from A to B, then I can relate some things from A to B like marks of the student from class 12 and class 11, or the age of the student from class 12 and 11, or the greater height between of the class 12 and class 11. For example, let's suppose I am taking the height of A is greater than height of B. Let's suppose where A is the student of the class 12 and B is the student of class 11. So let's suppose I'm taking few examples. So in the case of few examples, let's suppose the ordered pair like this, A and B, and this is the member of A cross B, the member of A cross B, and the relation between A and B is A R B. Now we will define this relation R. Let's suppose I define this R. So R is equal to height of A is greater than height of B. Height of A greater than height of B, means height of B. So likewise many more I can take the relation, like I can compare what in the A means what. This small a means this is the student of class 12, and B means what? This is the student of class this 11. And what about the function? Function is nothing but it is the special kind of relation. We will discuss later on. The special kind of relation. Then binary operation is there. So in the binary operation, we take two numbers and then we discuss about the operation, different operation like addition is there, subtraction, multiplication, division. So that is all about the binary operation. We generally binary operation we don't denote it by this is like this star mark. So this is all about the introduction of this chapter. Now we'll discuss relation. So what is the relation? As in the introduction already I had given that two sets are there. In the set A, they are the students of class 12, and in the set B, the student of the class 11. So and the if anything we are comparing, so that will be in the case of the relation. Now we will see the types of relation. Let's suppose I want to discuss types of relation. Types of relation. So many relations are there in the types. Types of relation, in the first one is your empty relation. This is the first one, and it is your nothing but empty relation. Empty relation. Second one is universal relation. Universal relation. This is the universal relation. Then your third type. The third type is your reflexive relation. A reflexive relation. Reflexive relation. Then symmetric relation. Symmetric relation. Symmetric relation. Symmetric relation. Then next one is the transitive relation. Transitive relation. And lastly is the equivalence relation. Equivalence relation. Equivalence relation. Equivalence relation. So I will discuss one by one. Okay. Let set A is given. And I want to define the empty relation. So empty relation means what? Suppose I denoted the empty relation by R. So if the R is equal to phi of subset of A cross A. If in the A cross A no element is related, means this phi indicate this one, no element is related. So this indicate what? This indicate that in A to A it is the empty relation. Now the next one is what? Next one is universal relation. So what is this universal relation? Let's suppose I denote it by R. So R is equal to A cross A. So this, in the case of this universal relation, all element of A is related to all element of A. So that is the universal relation. Now the next relation is your reflexive relation. In the reflexive relation, suppose A and A is given ordered pair A, and this is this is the member of this R. So A or A, it is a member of R. In this case, it implies what? And where your A is the member of A. A is the member of A. Then this relation is called reflexive relation. Now come to the symmetric relation. In the symmetric relation, what will be there? Let's suppose A1 and A2 is there. A1 and A2, this is the relation R, A1 and A2. It implies that what? There is also the relation between A2 and A1. A2 and A1. This is also the member of R. Okay. Then this where this A1 and A2, these two are the member of set A. Then this is called the symmetric relation. Means A1 and A2 is there. A2 and A1 is also there in that relation. And A1 and A2 is the what? A1 and A2 is the member of set A. So this is called the symmetric relation. Now the third one is transitive relation. Mind it, in the transitive relation, there must be three elements must be there in the set. At least three elements must be there in the set. So transitive relation, let's suppose A1 and A2, these two are the in the relation R, and A2 and A3, this is also the member of this relation. A1, A2, A3, and this implies what? A1, A2, A3, and this implies that A1 and A3 is also in the relation R, A1 and A3, where these A1, A2 and A3, this must be your member of your set E. So that is the transitive relation. And what about the equivalence relation? If any relation in which the relation is reflexive, symmetric and transitive, then that is called the equivalence relation. Means this must be what? This must be your reflexive. This must be your reflexive. This must be your symmetric. This must be your symmetric. And this must be your transitive also. This is transitive also. If any relation that is reflexive, symmetric and transitive, in that case what that relation is called the equivalence relation. I am taking one example to understand this. I am taking one example. Let's suppose a set A is given 1, 2 and 3. The set is given 1, 2 and 3. And the relation R is given. R is given means ordered pairs are given. Like this, suppose it is given like this. 1, 1, 2, 2, 3, 3, and then your 1, 2, 2, 1, 1, 2, 2, 1, and let's suppose 1, 2, 2, 1, 2, 3, like this. Suppose the ordered pairs are given like this, and we want to see which relation it satisfies. See, first thing is what? First thing, 1, 1, 2, 2, 3, 3 means here it is, A and A. So, see here all this given. So, that means what? It is a reflexive relation. And 1, 2 and 2, 1 is also given. So, that is your symmetric relation. But this is not satisfied here for the transitive relation, because in the transitive relation there must be A1 and A2 form. So that is not here. So that means it is not the transitive. Since it is your reflexive and symmetric also, then it is not the equivalence relation. So these all are the types of relation. Now the next one is your function. The types of the function are your one-one or injective, on-to or surjective, one-one and on-to or bijective. Then we will see the composition and then inverse. So how we define the one-one or injective? Let's suppose two functions are given. Let's suppose I am taking this one function. Suppose this is your one function. I call it x. And another function, I have the another function. Let's suppose I call this y. So x and y. These two functions are given, and I want to explain what is one-one. So let's suppose in the x we have the members. This is suppose 1, 2, 3, 4, and here are the A, B, C, D, E, like this. So suppose there is a function in between x and y, function in between x and y, f, sub f is there. So what is happening? So for the function case, what is there? For the function case, there is whatever the elements of x, for every element x for x, there must be image in y. So let's suppose it is like this. 1 is connected to A, 2 is connected to B, 2 is connected to B, 3 is connected to C, and 4 is connected to D. Let's suppose this one. I want to explain the 1, 1. This is in the case of 1, 1. Or call it injective. Injective. So see what is happening here. You can see easily that all the elements of x is related to y, and the images are different. The images are different. So then it is called the 1, 1 injective. So this is your 1, 1 function. Now let's suppose the second one is your on-to or surjective. Mind it, in the 1, 1, there is one element is left here in the 1, 1. And the images of x is in the y. And one element also left there. Now come to the on-to. On-to, let's suppose I am taking this, let's suppose this is the x one, and here I have y. This is the y. X and y. So the element in the x is, let's suppose the elements are A, then we have the A, then B, and then C. Let's suppose B is also there. And the y, the elements are your what? The elements are your, this is suppose 1, 2, and 3. Now I want to define what is the on-to or surjective. On-to, or this is your surjective. So in this case, always remember every element of x is related to y because it is a function. And another thing is that no element will be left here. Means whatever the element in the x, so every element of y must be related to every element of x. No element will be left. See, while in the case of injective, there may be some this element will be left. So let's suppose A. So it is A to 1. Suppose this is B. suppose again B21 is there, then C, let's see, this is 2 and B let's say is related to 3. So you can clearly see here A and B both are related to 1. So we can see here whatever the relation between F and Y. So every element of Y is the image in the X. Means we can also say here like this f of Y, suppose I am taking, so that f of Y is related to this element here, X. So this is your onto, or we call it surjective. In the injective there may be any element left, but in the case of this surjective, must be every element of Y must be related, have the image, every element of X has the image in the Y. Fy is equal to X. Now one more is there. When you combine this, so by means what? By means your this both. So by 2. So there must be one more is there, and that one is your what? 1 1 on 2, and that we call it what? That we call it bijective. Okay. So third one I am taking the bijective. Let's suppose one element is here, one element. Suppose one set is X is here. Let's suppose another set is Y. This is set Y is here. So I want to find what is the 1 1 and onto both means bijective. So I will define here what? I will define here 1 1 by bijective. 1 1 and bijective. 1 1 onto 1 1 and onto. Its name is what? 1 1 and onto. Also this is called what? This is also called here bijective. Bijective. This is also called bijective. Bijective. Or also called this. So let's suppose I'm taking few examples. Suppose X, in the X the elements are here A, B, C, and here it is D. And in the element in the Y, there is also numbers are there. This is your 1, this is 2, this is 3, and this is 4. This is the example of 1 1 and onto, or we call it bijective. A is related to 1, B is related to 2, C is related to 3, and D is related to 4. This will be there. We start the composition. So in the case of composition, there are two functions. Let's suppose X and Y. There are two functions. Better we can take A and B. So let's suppose the function, one function is it is from A to B. This function is from A to B, and another function is, let's suppose G, and this function is from B to C. This is from B to C. So one is from, this is two function, and let's suppose I want to find this composition of F and G. Composition of F and G, let's suppose I find it. So composition of F and G, this is your denoted by what? This is denoted by G naught F. This is G naught G composition of F. This is defined by that one. So we have the one function that is your A to B. So let's suppose the function A, and then let's suppose this is the function B, and one is the function C. The function C, A, B, C. These are the two functions, A, B and C. Let's suppose this is X and we have the function here. Suppose this is Fx and this is nothing but this is G Fx. This is G Fx. Now, from A to B, we have the function F, and from B to C, we have the function. This function is G. Then there is a function in between A and C. From this is from A to C, and this is denoted by what? This is denoted by G composition of F. So the function is A to B and this is B to C. So the function is defined as a what? F and G. This F and G, and this will be denoted by what? G not F. G composition of F. Where what is G not F? G composition of F. This is G composition of F, and this G composition of F is how we define that one. So G composition of Fx, this is defined by what? This will be defined by G, then function of G function of Fx, like this. It will be defined like this. So here is the three A to B given function, then B to C is given, then composition will be defined as what? This will be defined as a C to A. So that is means what? That is means A to C is there. So this is your G not F, and this is your nothing but this is your A to C. So this is all about the composition. When the function is given A to B, function A to B, function F, then B to C, that is your G, and then the function is from A to C, and this is denoted by G composition F, and this is from A to C. And how it will define? It will define as a Z naught G composition F, and this is equal to your G Fx. So this is the composition. Now for the last one, that is the inverse. For the inverse case, let's suppose I am taking a function f, and this is from f is from x to y. This is from x to y. This function is from x to y, and so that's from x to y. There is inverse is there. So for the inverse case, let's suppose g is the another function. This is the another function, and this suppose it is in the y to x. Let's suppose it is from y to x. From x to y, and g is from y to x. And let's suppose I want to find inverse. Let's suppose I find. So that what is mean for the inverse case, g, if I find it g composition of f, the composition of f, if I got it, the value of this I got it ix. So that means what? That means the inverse case. Similarly, if I have just reverse of this one, F composition of G, F composition of G, suppose it is given, and the value is your IY, that means it is the inverse. So in this case, the function F, it will be called inverse, and this is denoted by, inverse is denoted by F, this is F minus 1, like this. So this way we denote the inverse F, and it is denoted F to power minus 1, and this is denoted by inverse. So F is the x to y is there, and G y to x is there, y to x. So G composition of F, suppose I am finding and I am getting Ix, and again I am taking F composition of G, I am getting Iy. That means what? That means the function G, that is function G, this function G is called the inverse of F, and it is denoted by F to the power minus 1. Now see the case of the last one is the binary operation. In the binary operation, we'll give the definition. Then we'll discuss about the commutative, associative, identity, and then inverse. So what is the definition? So let's suppose set A is there, and we define the we want the definition of the binary operation. Let's suppose I denote it by this star. So this star will be nothing but this is your A cross A, and this is equal. This is the set A, which is A2A and A. This I denote it by this binary operation. So let's suppose the ordered pairs are A and B. So for the binary operation, we denote this A and B as the binary operation, this will be denoted as A, this is star, A star B. So this will be the binary operation in between A and B. Now this star may be your plus, it may be negative, it may be your multiplication, division. Under this it will define some other numbers, like suppose I can write it in this way. For example, I can write it this way: A square plus B square. I write in this way also. So this is all about how the binary can be represented. Now you will say the commutative property. Commutative property is this is the same property as we had seen in the case of multiplication or this addition. So commutative property means what? So again, suppose the operation A cross A, and we have the A and B as the. So commutative means what? This commutative means A operation B, this is equal to your B operation A. So that property is your commutative property. Means let's suppose I am taking 2 and 3 and plus I am taking. So what will happen here? 2 plus 3, that is 5, and again 3 plus 2, that is also 5. So this is the commutative property. Suppose I am taking the multiplication case, that is also true for commutative. 3 into 2, 6, and 2 into 3, that is also 6. Now come to the next one. Next one is the associative property. In the associative property, always remember there must be three numbers must be there. So in the associative property, I can write it how? I can write it A star B, and this is star C. A star B star C, I can take it in this way. First I am taking the B star C, or I will take the A star B, and this is star C. Suppose in this way. So you will find that the associative property is true for suppose addition is given. In that case also it is true, and simple multiplication is given. In that case also it is true, but for the other number, for other operation, it depends upon the value of A and B. Because A and B, you can take anything, A square, B square, or you can take A plus 2B, or any number you can define. Now, next one is what? Next one is your identity. What is the meaning of identity? Identity means, suppose you are taking any number, suppose you are taking, and suppose I denote it by let's suppose identity E I am taking. So how I define the identity? So in the identity case, suppose E is the identity, so A, and then I am taking the A star E. Suppose I am taking that one. So in this case, what is equal to? This is equal to your A, and this is also equal to your E star A. So if you get in this way, so you will get what? You will get the identity. For example, let's suppose I am taking number 2, I am suppose taking. So if you multiply 2 into 1, I will get 2. And now 1 into 2, again I am getting 2. So here the identity for E for multiplication is equal to 1. Likewise what? Likewise I can take your what? Or I can take the A plus 0. So A plus 0, this is your A, and again your this your 0 plus A, again A. So 0 is the identity for, in that case it will be the identity. Now come to the inverse. Inverse means what? Let's suppose a number A is there, and I have in the inverse case I have A star B. I am getting A star B. If I get A star B, suppose I am getting the identity E, then or your this B star A. In that case, I am getting the identity. So in that case, it is called the inverse. For example, let's suppose I have 2 is there. So 2 is there, and if I put it here minus 2, so I will get what? I will get the 0. So that means what? That is the minus 2 is the inverse of what? Addition. Of addition, the inverse A. Let's suppose I am taking 2. I multiply it by 1 by 2. So I am getting the identity of this multiplication. So 1 by 2 is the inverse, or you can say is the reciprocal. You can say in that way also. So this is all about the binary operation. Thanks for watching. If you have any doubt, write in the comment box. If you like my video, please like it, subscribe it, and share with your friends. Thank you.